Okay, so this lecture will be about searching and sorting. Two parts. We'll cover searching today, we'll cover sorting on Wednesday. So the basic idea with searching, pretty simple. You want to have data arranged in some way where it's easy to find what you want, right? And a classic example of this that you have perhaps seen in your grandparents' homes is the phone book, right? So I'm going to assume everybody's seen a phone book at some point in their lives, even if they haven't seen one recently. So the way a phone book works, as you know, if you know someone's last name and their first name, it's pretty easy to find what you're looking for. Okay? Now, this is the point in the semester where once upon a time, perhaps I might have said, it's really fast and easy, like your best friend's sister. But of course, you know, yeah, we don't say that anymore. It's inappropriate. Anyway, so if you know somebody's last name and first name, it's easy to find what you're looking for, okay? Because you just flip to the proper page, then you get to the correct column, then to the correct entry, right? And then you find what you're looking for that way. However, if you don't have the name, for example, maybe you just have the address, well, the phone book won't be a whole lot of help because it's not sorted by addresses, is it? No, so if you had just someone's address and you wanted to find out the number with just an address, you'd need to look through every entry in the phone book to eventually find the matching phone number. Okay, so this is what's called indexing. Indexing is a way that you can provide a simple way to focus on things. Now, the way indexing works ideally is you can have some sort of numeric value for it. So suppose, suppose you have a massive stack of invoices indexed by invoice number, okay? Well, in that case, it's pretty easy to find what you're looking for if you have the correct index number, right? Because no matter how big this is, even if this table is stretched across many, many other tables, right? Even if it's a very big thing, you could say, oh, well, this table here, this particular database device, this hard drive, has indexes, invoices 1 to 100 million. And this has 100 million plus 1 to 200 million. And so on. Over here, we have what? 500 million plus 1 to 600 million. So once I know what the invoice number is, I say, okay, I can pin it down to this one. Likewise, each of these hard disks has a bunch of what are called tracks on it. So if I know the correct, however the data is arranged, it could be arranged in a bunch of files, right? So there could be files for every million or even fewer, right? For every, like, say, 10,000 records. I can find the appropriate file that I'm looking for. And once again, I don't have to search through all of these 600 million entries to find the thing I'm looking for. I can say, oh, I know just by the number, it's on this device. I also know just by the number, the name of the file that it's stored in. Ta-da, I can very easily locate this thing. All right, so indexing is very important. Indexing allows you to quickly find data. Let's see, we got some more chat. Yeah, okay. So that's it. That's what we're going to go. Now, again, it's easiest to think about this in terms of numbers. It's easiest to think about indexing in terms of numbers, but it works for any scheme that is convertible to what are called, an ordinal series, to an ordinal or a sequential numeric series. For example, oh damn, I didn't mean to do that. That was freaky. I just found a new feature. Sequential numeric series or alphabetized. Alphabetized text data. Okay, as long as you can come up with some sequence of saying this thing comes before this thing in all cases, yeah, you can do this sort of system for it. But again, it's easiest to think about just in terms of numbers. All right, so here we get into the slides. So what we'll do searching algorithms on some small arrays. We'll talk about the two main approaches, linear and binary search. And then when we come back on Wednesday, we'll talk about selection and bubble sort, and the big one, heap sort, and then a little bit of follow-up around that. Okay, so suppose you have a big pile of data. Like I said, big stack of invoices, big stack of anything, really. And what you want to do is set up some process where you can find the stuff quickly. Okay, so let's say we're looking for a particular invoice in the array. So the invoice has some number X, and we want to either find the location of that invoice X in the array, right? What index of the invoice array stores that particular one, if it's even in there. And if it's not in there, we want to get some signal that, yeah, we looked for it, we found it, and it wasn't in there. Okay, so essentially, we know any array will have the lowest index value being 0, so we can use -1 as a safe code for the thing is not found, right? Because we know no array index will ever have a negative value. And we also make the assumption that there are no duplicate values in the array, right? We don't have two invoices with the same number. Okay, so based on that, we're going to evaluate a couple of different algorithms according to how many comparisons they have to do. Essentially, how many checks they have to do in the database to find what they're looking for. And we're going to look at two sides of that. One for how hard it is to find something if it's there, and another for how hard it is to find something if it's not there. Okay, so successful search, both of these algorithms are going to be complete in the sense, yeah, they're going to always work. They're always going to find the thing that's there, but they're only successful if that actual X value is in the array. If it's not in the array, you can't find what index it's at. That would be an unsuccessful search. Okay. So the first one, we have this little array, and it's small enough that we can just eyeball it, right? It just has 9 elements. We can eyeball it and say, okay, suppose we're looking for the number 45. Look, scan through it left to right. There's no 45. We would return -1, the not found constant. Or if in a successful search, we'd say, oh, look for 12. Okay, there it is. It's at index 4. Boom, found it. Okay. So we return index 4, the index of the element where the 12 value is stored. All right. So the basic way linear search works, it's a simple start at one end, scan the array all the way to the other end. When you find the match, return the index. Okay, so here, if we were going to do some code for this, the search code actually works. We'll get to stuff later for us that has some pseudocode. It's not quite complete, but that's okay. All right, so linear search, we send along a reference to an array. The array is called number. We also send along the value that we're looking for called search value. And we start off the first index loc as 0. So that's where we're starting our search. And as long as loc is less than number.length, right? As long as loc is looking at a valid index, something less than the last index of number, and number at that index doesn't equal search value, we go on to the next one. We increase loc. Okay, so we're going to keep on doing that. As long as we don't find the search value, then we're going to just increase loc to look at the next index. However, if loc equals number.length, right? If we find that match, if we don't find the match, if we reach the end of the array and we haven't found a match, then we return the not found code. Otherwise, we return the location, right? We return the index where we actually found the match. All right. Now I'm going to mention right off the bat, there's some interesting stuff here with algorithm design where you can make stuff, the choices you choose, the sequence of activities, actually can make a significant difference on how fast algorithms run. So one point here, I'm just gonna mention this as something to look out for. We have this, right? While loc is less than number dot length. Well, we're going to do that, right, on many cases. We're also going to do this on many cases. But here's the thing. This will have to do on every, right? This will have to do, as long as we're searching, we'll have to do this. This one we'll only have to do up until we find a match. So if the value isn't in the array, we're going to do these for every index in the array. However, if the value is in the array, right, then we can save a tiny bit by checking this first, right? We can check and see, oh, is there a match? And if there is a match, we're going to save that tiny, tiny bit of, you know, machine cycles. It's going to be really trivial in this case, but I'm going to say, you know, for algorithms like this, the order in which you do things often matters, right? Sometimes, well, this is a common thing in systems all over, right? You can achieve the same goal a little bit faster. So always, you know, again, at the scale we're doing, it really doesn't matter. We're like saving a few microseconds, but well, anyway, the real experts in code, they just kind of do this reflexively. They automatically think about designing code to run in the fastest way possible. All right, so that's a footnote. Okay, so for linear search, we can analyze it in two ways. First of all, the successful search. In the best case, we find it right away. The value that we're looking for is at index 0. We do one comparison, boom, we find it, we're done. In the worst case, we have to go through the whole array, right? We find it at the very end. So the average for this is going to basically be n over 2, right? If n is very large, then the number of comparisons we do in a successful search will be n over 2. In an unsuccessful search, no matter what you do, you got to compare everything, right? You got to check every index in the array to see if the value is there. You're not going to find it because we've already specified it's an unsuccessful search. So it's going to require n comparisons. So on average, the number of comparisons this linear search is going to require is going to be somewhere between n over 2 and n, depending on how often the search is successful or unsuccessful. Okay. So maybe that's not too bad, right? If the array is small and these comparisons are taking microseconds, yeah, that's okay. We can live with that. But here's the thing. If n is large, like say in the billions, and the comparison process is a bit more challenging, maybe it doesn't take microseconds, maybe it takes milliseconds, well, doing a billion comparisons is going to take a while, right? Doing a billion comparisons on something that takes a millisecond to go through, that basically means your operation is going to take 1,000,000 seconds. So you want it to be faster. Well, let's look. When things are indexed, you can do what's called a binary search. Fundamentally, binary search is it's a convergent algorithm. You know if something is in there or it isn't. All right, let me give a simple example. Back to our phone book, right? So suppose this rectangle indicates phone listings, right? Represents phone listings. Let's say represents. Now, suppose the thing I'm looking for is here, right? I'm going to draw a little tiny circle for it. Ta-da. That's what I'm looking for. It's there. So if I wanted to find it, and let's suppose I didn't have any guide to the distribution of names, right? Suppose I have no idea how names are distributed in the phone book. I don't know if one letter is more common than the other, things like that. I have no idea about the distribution, right? Because if I did have an idea, I could search a little differently. Let's say I don't. So the first thing I would do, I'm going to search here right in the middle. And what do I know? I know that it's either on this side, either on this side, or on this side, right? Well, as it happens, right, I know that it's on this side. I can verify that because I know that this is a ranked thing. Suppose this name here, I don't know, is Violet, not Violent, Violet, what's the last name starts with V? Violet Vaughn. Okay, so she's got her entry in there somewhere over at the V's. So I know when I see this, I see something like, you know, M. And I know that, okay, it's not going to be on this side. So I can black this out. Boom, it's not over here. So I search again. I search about halfway through. And same thing, right? I know it's going to be on the left or on the right. Well, again, suppose I look at this one and I say, okay, this is S. Well, I know V comes after S in the alphabet, so kaboom, that's all out, right? I do one more search. I look right down the middle here, and instead of VI, right, maybe I find VO. So I know, boom, it's not on that side. And gradually I converge back and forth until I reach the point where finally I find this, right? But unlike in the linear search, finding this, even if n is crazy big, like let's say 1 billion, I can eliminate half possibilities with one single comparison, and half of what remain with each successive comparison. Okay, so the first comparison, right, 1 will get rid of 50%, 2 will get rid of 75%, 3/4, 3 will get rid of 7/8, 87.5%, right, and so on. Very quickly, I'm cutting into this, right? So if n is 1 billion, with just 3 searches, I've eliminated 875 million options. Whereas with a simple linear search, I would have eliminated 3 options. Okay, 875 million is a lot bigger than 3. So for large arrays, this kind of binary search is extremely efficient. The only thing is, it requires that the data be sorted, right? So I know that everything on this side is equal to or greater than VO, and everything on this side is less than or equal to S. If you don't have that kind of sequential arrangement, binary search doesn't work. All right, but let's talk about the mechanics. We're going to bounce back here, back to the slides. So suppose this array is sorted, right? And the idea here, we search the value in the middle position, okay? We first go to the middle, index 4, right? So the middle index. If the x, the number that we're looking for, is less than that value, then we search the middle of the left half next, okay? Otherwise, if x is greater, then we search the middle of the right half next. All right, so let's do a couple examples. So first one here, okay, we're searching for the number 44. And this is a sequential search. We can quickly verify that 44 exists in the array. So we start off, we find the middle index. Well, middle is the average of high and low. Also notice we're doing Java math here. So these are both ints. So when we divide by 2, the fractions go away. So we started at the middle one, right? We know when we check for 38, we say, oh, 38 is less than 44. Therefore, index 4 and every lower index can't have 44. We know it has to be in index 5 or up. So 5 becomes our new low value. Okay, so here we are, 5. Our high is still 8. We take the average. In Java, 5 plus 8 divided by 2 becomes 6, right? 6.5, but drop the half. So our comparison point is now index 6. That's our midpoint. We look at our array. We say, 44 is less than 77. If it exists in this array, it must be to the left of index 6, right? So the only place where it can hide out at this point is index 5. Well, our low is 5. Our high is 5. We average them together. We get 5, we do the comparison, 44, we find it, yay. Okay, so linear search would have taken 6 comparisons to find 44, right? We search from 0 and go on. This case, even in a small array, we get some savings, only takes 3 comparisons. Okay, unsuccessful search, similar process. So let's say we're looking for 45, which we can verify does not exist in this array. So again, we start at the middle. Index 4, value is 38. Well, 45 is greater than 38, so we know if 45 exists in the array, it has to be at index 5 or higher. So 5 becomes our new low index. Then we do the same thing. 5 is our low index, 8 is still high. 5 plus 8 divided by 2, Java math, it's 6. So 6 becomes our point of reference. Well, 45 is less than 77. So we know if 45 exists in the array, it has to exist to the left of index 6. So the only place where it could exist now is index 5. 5 becomes our new high index. Okay, so we do the comparison. 5 is the low index, 5 is the high index, 5 is therefore the middle index. We do the comparison and we find 44 is less than 45. So we know if 45 exists in the array, it has to be to the right of index 5, right? It has to be 6 and up. So when we do the squeeze on this, what do we recognize? Well, our low is 6 and our high is 5. Our low is greater than the high. We've squeezed out past the point where, this can't be it. We got down to one index where the thing could be, it wasn't there, and high and low got switched around. So our low is bigger than our high. That's how we know there's nothing left to search, okay? And we give up. So again, in the linear search, it would have taken us 8 comparisons. Here for our binary search, it only takes us 4 comparisons, and then we're done. 3, depending on how you look at it. Okay, so much quicker. And here's some code for that. If you want to see how that works, that's fine. Okay. Now, how well does this work? Well, in the best case, we find something right away. We find one comparison. But in the worst case, we have log base 2 of n, where n is the array size. So since every comparison gets rid of half the possibilities, we take the log base 2, essentially how many powers of 2 are in n, and that's how many steps it's going to take. So if, say, n is 1,000, right, our log base 2 of n would be 10. That's an easy one to remember. And for every multiple of 1,000, right, every factor of 1,000, we add on another 10 steps. So 1,000,000 is 1,000 thousands. It would require 20 comparisons. 1,000,000,000 is 1,000 millions, so it would require 30 comparisons. Successful search is much, much faster. In the case of the unsuccessful search, we simply do the same process. It's just going to take log base 2 of n comparisons. That's how we get to the point where we squeeze all the possibilities out and flip around the low and high. And at that point, we know it can't be in there. So log base 2 of n, once again, is going to require about 10 per factor of 1,000. So 10 for 1,000, 20 for 1,000,000, 30 for 1,000,000,000. Okay, so much, much faster. You want to do the comparison for, here we go, even for 10,000, it's very big, right? So the difference, if the linear is going to take 10,000 comparisons, they have here log base, oh yeah, because 1,000 is 10. Log base 2 of n to do 1,000 will take 10. 10,000 would take like 14. Much, much faster. Okay, and it keeps getting much, much, much faster as the size of the arrays get bigger. Linear search on a 1,000,000,000 item array would take 1,000,000,000 comparisons, whereas a binary search would only take 30. This is what enables these large data structures to exist and be useful. Okay. So that's it. That's what there is to say about searching. Searching is pretty easy to understand, I think. Sorting gets a little weird. We'll have more to say about that next week. But this is it. This is it for searching. There's a linear search, which is slow. Sometimes you might use it if the array is really tiny, like say less than 10 elements, then you're not going to save that much doing a binary search. And it's a little bit more of a hassle to set up. You can look at this and see, yeah, the code is just a little bit more complicated. Right, so we can look at this. This code's a little simpler. Okay, so if the array is small, you're not going to save that much time doing a binary array, so binary search. So you might just go ahead and do a linear search once they get down below a certain threshold, like say 10. And at that point, the time savings are going to be trivial anyway, because, you know, again, it's going to be microseconds for both of them, unless you're doing a whole lot of those operations all the time. Okay. Questions on any of this? How's everybody doing? I'm going to stop the share. I am going to stop the recording. Kaboom. That's strange.